Okay, so let us continue. So where we were at, right, last time was that we finished, right, discussing, the common characteristics, right, of discrete random variables, namely mass function, PMF, right, mapping to like a function of a discrete random variable, uh, combining discrete random variables using sum, difference, that kind of thing, and then expectation and variance, right? And higher moments, covariance. And then, right, we moved on to basically now dealing with very specific, right, discrete random variables that must be known, okay, by anyone who studies anything related to probability. Because these are well-known models that basically are usually the building blocks for more complex models. So you would encounter these again and again in any, right, basically probability slash statistics slash machine learning, whatever, right? As long as they start to employ probability, chances are you will see some of these, okay? And so that's why you must memorize, just like, calculus, right? You must memorize certain things. So here you must memorize the mass function, expectation, the variance. The parameters are part of the mass function, so kind of it goes in there. And right, I guess here, just trying to be polite, but this is for 77 students, right? Meaning that on the exam, right, you're expected to memorize this. The only single exception, as I mentioned, is the hypergeometric random variable, where you don't have to memorize the variance, right? But anything else, you'll have to memorize. So we talked about the Bernoulli, right? And this is the mass function, expectation, variance, how the Bernoulli serve as the indicator function. Then we talked about the binomial. This is the mass function, how the Bernoulli and the binomial are connected, right? That is sum of IID Bernoulli is a binomial, and the Bernoulli is a special case of a binomial, right? So this allows us, right? This connection allows us to derive this very easily, right? Using the law of expectation and variance versus, right, having to go through the definition and derive this, as I showed you last time. It's an educational exercise, but it's not something, let's say, that you need to memorize unless you want to be skilled, right, in analytical derivation, which is a good skill if you do math in general. But probabilistically speaking, right, this way of deriving is more recommended because it shows a more probabilistic connection between things. And then, right, we skip this, right? Multinomial distribution actually is very important, but kind of you'll see that more in stochastic processes and things like that. And you should look at yourself, right? But we won't harp on that in this course. All right, so the next one, right, is the hypergeometric, right? So first of all, this is the mass function, okay? And this is the model, right? And so again, the model is pretty simple. It's the good old EARN that we usually deal with, where, right, the K of them that is blue, the remaining one, let's say red, right? So N here represents the total, right, in the EARN. And you select, right, N without replacement, right? And you want to check how many blues is in your sample, right? So long story short, this is sampling without replacement in a finite population, right? The population being the EARN, you sample without replacement, okay? And so the hypergeometric might seem very mundane, right? This is just commentaries, right? Uh, in its own story. It's interesting, but so why? The answer is actually right. There is its close cousin. In other words, the binomial, right, that we just talked about. That is, if we tell the same story, but just change the word without replacement with replacement, then the distribution, instead of the being the hypergeometric, will become a binomial. Okay, and so it just goes to tell you that that's why you kind of want to pay attention to hypergeometric as a, let's say, a dependent, right, example right next to the binomial. And also to show you, right, I mean, there are all the interesting connection, like, here for large n, right, for large population, right? This is the population size in terms of, the language of statistics, right? Then, right, sampling with replacement or sampling without replacement are similar. Again, right, has implication in sampling in statistics, but you can see the root of it, right, or the explanation for it coming from probability theory. Okay. Anyway, right, but any questions so far? So let's go back to the description of the hypergeometric here, right? So as we say, right, this is the PMF, right? But let's say right away, right? Is this a complete description of the mass function? Have we described everything? Is this a complete description of a mass function, or is something missing? Well, the answer is no, right? Something is missing. What is missing? What's missing, right, is the possible range of values, right? Namely the support of the random variable, right? This is always there. When you look at the PMF, you kind of tend to zone into here, but you kind of ignore this, right? Kind of, I guess, by default. But that's actually wrong. The reason is, right, without the support, right, then actually the PMF is not valid in the sense that, right, you can only get a legit PMF if you sum over the support to get one, right? If you list the support incorrectly, then this actually by the same nature, by the same consequence, cannot be a PMF because the sum won't be one, right? So the formula for the mass function and the support must go together. You must know what range of value you sum over, right? Or in other words, what values the random variable can take. So having said that, right, why don't we list it here? Or what are the values that the random variable can take for hypergeometric? Is it just simply this, right? That we just simply forget to put it on? Is that true? just like the binomial here, right? If it's a binomial, when we sample with replacement, then, right, the value is from 0 to little n, right? Is that the same case here? Oh, the answer is no, right? The range of k here is actually a bit more complicated. K here depends on the interaction between these parameters. So let's give an example. Let's say you have, right, 3 blues, and let's say you have 7 balls total, so 4 red, right? And let's say I sample 5, right, out of this. So out of 7 balls, I sample 5. All right. So is it possible for k to be 0 here in this scenario? Is it possible for me to have no blue ball in my sample? The answer is no, right? Because there are 4 red balls. So at most, right, I can have 4 red balls in my sample, which means I have to have at least 1 blue, right? So k is bigger than or equal to 1 in this particular example. Do you understand? So for that reason, right, the support of the hypergeometric is like this, meaning that, right, the upper bound is by the sample size and how many blue balls, right, and the population size, right, the population group that you're sampling that you want. So it's bounded by those two. Similarly, right, the minimum, of course, is bounded by 0, but it's also bounded by this. This is nothing but, right, the remaining blue balls if you have taken away all the red balls. So that's why, right, the support of a hypergeometric must be this, between these two values. Any question? All right. And so now, when we talk about the mean and the variance of the hypergeometric, the mean, right, is this. And note, right, is exactly is the same as this binomial with replacement, right? Notice if we have a binomial like this, then expectation is n times p, which is nk over n. And that's how you can remember the mean of the hypergeometric. Okay. So why? We have emphasized, right, that if it's not a binomial, why is the expectation the same? No, right? If you sum, let's say between these two values, which is already crazy, k, right, over n choose n, k choose k, n minus k choose n minus k, right, over this max and this min. The point is, the answer is n k over n. You should appreciate that a little bit. Now, if anyone wants to earn an A in this course in 5 minutes, prove this to me. I promise you I'll give you an A for the course without taking any further exam. Want to try that?
I'm interested.
5 minutes, prove it.
Oh, could you uh say again like the bottom and the top of the sum, the min
So,
max?
yep, the max is because of
Oh, because of the sample size larger.
right, this is the most red balls you can have in your sample. Therefore, right, you must have that much blue, right? Of course, this is only if your sample size is larger than the number of red, the maximum of red. If this is less, then 0 will be upper bound, right? And of course, the same.
Oh,
All right, you have 5 minutes to prove that to me. Okay, counting from right now. Okay. Anyone else interested? All right. So only one candidate. All right. So now, right, while one person is trying to get an A without having to take further exams, let us look for an easier way to do so, which is, right, to use the probabilistic technique rather than, using the analytical, right, approach. And so what is the point here? The point here is that if you represent, right, the outcome of individual ball being picked, right, as blue, then, right, if you sum it up, it still represents the total number of blue balls, right, in the sample. Okay. And individually, each of them is still a Bernoulli because, you just say it's 1 if it's blue, 0 if not, with success probability being the ratio, right, of the blue and the total population. Okay. And now, the reason why, right, all of them have the same success probability is, remember that this is exactly like the hat problem, where, right, the point of view of each of the ball, right, is not influenced by the information you might have about another ball. And of course, these are dependent. So this is very reminiscent of the hat problem, right? These are dependent. Okay. But that doesn't matter when it comes to finding expectation of the sum. Why? Because of this rule. Right? The expectation of a linear combination is the linear combination of expectation for all random variables, whether they're independent or not. Okay. And so that's why, right, when we break it down to the sum like this, we can just apply the expectation formula. Okay. And of course, right, all of them being the same, That's k over n. And how many of them? There's little n of them. So that's why it's the same as the expectation for the binomial. Okay. Now, when it comes to the variance, right? Note that what is the variance of the binomial corresponding to this? The variance of the binomial would be n p 1 minus p, right? That's a variance. Now, what is the variance here? N p 1 minus p and this term. Why is it there? It is there because, right, exactly, these are non-independent. That's where you see the non-independence show up, right? In the sum, but only in calculation of variance. Because independence, right, doesn't affect calculation expectation of the sum. And so exactly, right, that's why the variance of a hypergeometric is not the same as the variance of a binomial corresponding to a situation when you sample with replacement, right? Now, admittedly, this formula is slightly complex to remember, so that's why I don't require you to memorize this. But if you look at a structure long enough, right, you'll see that it's easy to memorize, np1 minus p, with an extra term that you have to memorize. But that's fine, right? I'm not going to require that. Any question? All right. Were we successful to prove that?
I don't think I got like the whole thing. I was just thinking about simplifying the
K and n choose k, k choose k, right? This and that.
yeah, the yeah, that part. But
Yeah,
it's because the sum doesn't start from zero. But yeah.
exactly.
Yeah,
Absolutely.
I think I'm gonna think about it. Like even though it doesn't count, I might just like email you
No,
something.
it's great. I'm very, very, very glad to see you're interested. I meant that as a joke, of course, right? If it's not easy, then, but the point is, right, that I want to just use that to draw your interest, the point that this is actually not a non-trivial calculation. Exactly, the painful thing is about the two bound, as you point out, exactly, right? The two bounds here kind of get in the way. And I myself haven't seriously thought about how to take care of that either, right? But yeah, right, those two bounds seem very, very painful to deal with. And let me say that this structure doesn't seem that nice either. But yeah, I mean, I guess you can manipulate it. So I guess here's a hint for you, right? You actually can try to convert it to another hypergeometric. I think that's the same trick, right? With k minus one or something like that. I think that's a trick, right? With the same binomial. So the bound will work for you that way. You kind of shift the bound, so the bound will move together with you. I think that's the way you do it. But yeah, you have to kind of analyze this structure a bit more carefully.
Okay.
All right. Yeah. No, it's cool. It's great to play around with this if you have time. It's another value that's kind of fun for math exploration. All right. Oh, so let us continue with the problem set. So I think this is the last question. Okay. Number 7. Right. So let's take a look and tell me what the answer is. All right, so this problem, right, is part of the group that identifying discrete random variable models, right? So if you let X be the number of defective, right, then what do we know about X? What distribution does X follow? So it's a hypergeometric, right? With what parameters? So we list n, right? K and little n in that order, right? So that would be 20, 4, and 3, correct? So expectation of X here will be 3 times 4 over 20, right? Whatever that is. Any question? So while we're at this, right, let me point out that, for example, let's say you say the answer like this. Then this answer is not complete, this one, right? Because you did not recognize that X is hypergeometric random variable, right? I'm not saying that this answer is wrong as long as you list out the probability correctly, but this fails to hit the point of the question, which is the recognition of a well-known distribution. You understand? All right. Any question about this? Okay. So the next well-known random variable we'll be looking at is the geometric. So the geometric, right, the model is to look at how long we have to wait until we see the first success. In an IID here, right, is the word that you see a lot. That means independent, identically distributed, right? What would be simple IID experiment to think about? You keep flipping a coin, or toss a dice. These are examples of IID experiment because, right, supposedly between the flips, things are independent. And then, right, it's the same coin, so they're identical, right, in terms of distribution. Right. So for example, right, in terms of a coin flip, the picture, right, is simple. You flip a coin with probability P, right, of getting a head. Then you wait, you look at how long until you see the first head, right? So the sequence is something like tail, 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 and then head, right? Equivalently, you could, if you, let's use the example of the dice toss, you could define a success as seeing like a 5 or 6, let's say. Then, right, in that in that language, then it's like the last toss, you get a 5 or 6. And all the previous tosses, you get 1 to 4. Is that okay? So all of these are geometric random variables, waiting until you see the first success, however you want to define that success in a IID experiment. And so, right, understanding that, then it should not be a surprise, right, to see that the support, the values that it can take, has to start with 1, right, and keep on going. Because, right, you need to have at least one trial to see one success. And, right, may or may not be surprising, but there's no upper bound, right, on how long you have to wait until you see the first success. So, right, do not confuse rare event. Namely, right, I don't think any one of us have witnessed, right, a sequence of coin toss that has 999 tails and then a head, right? Don't think so. Reason why, because it's super rare. But that doesn't mean, right, it's impossible, right? So that means they still form a part of the support of the random variable, even though, right, the probability of it being taken on those values are super rare, right, super small. Anyway, right, so the probability of, right, having to wait k trials, right, total, to see a success, right, is pretty easy because the last one must be a success, so it's p. All the previous ones must be failures, so it's 1 minus p, right? Well, so let's see how good your calculus 2 is. If our claim is true, then this sum must be 1. Right? Why is that true? Well, it is true, right? Because of the geometric series, right? If you sum 1 minus p to k minus 1, k from 1 to infinity, right? Then this is a geometric series with the first term as 1, right? Because when you plug in 1 here for k, you got 0, right? And then the ratio is 1 minus p. So it's 1 over p. So if you multiply 1 over p with p, you get 1. Right? Okay. Now, what about the expectation? So to compute, so first of all, let's talk about the meaning of the expectation, right? The meaning of the expectation actually is quite intuitive, right? In fact, it says that, right? For example, it just says this. Suppose, right, you toss a coin or you perform an experiment, right, whose success probability is 0.1. Then I think, right, it's a common statement. People say this without even backing it up with any reason. Let's say, yeah, then you have to wait about 10, right, tosses to see ahead, right? That's actually a common statement. Correct? Where would they get the 10 from? The 10 is from 1 over 0.1. So there you go, right? If you keep repeating, right, trials whose success probability is P, on average, you will need to do 1 over P trials before you see a success. That's what the geometric tells you. Okay. So now that's, again, right, just sort of common intuition. We need to back this up with mathematics, right? So what we need to show is why sum k p, sorry, 1 minus p to a k minus 1 times p, k runs from 1 to infinity, is equal to 1 over p. Anyone can explain this? All right. Actually, it's just a simple calculus trick. Well, maybe not simple. First of all, right, notice that because the p, right, is a constant, right, it's the same as showing this. Now the k and k minus 1, right, actually is a very appealing relationship of what? It's relationship of derivative with respect to p of 1 minus p to k, right? If you differentiate this expression with respect to k, you got k times 1 minus p to k minus 1. Well, right, you pick up a chain rule, so you actually get a minus 1 outside, minus sign. Right, so let's put that minus sign on the right-hand side. Right? Okay. Well, the next thing, right, we're going to recognize is, well, right, this derivative is respect to p, and the sum is over k, so derivative is linear, so we can pull the derivative operator outside. Right. And, well, anything else? Let's see here, right, when k equals to 1, that's going to be 1. Yeah, that's fine. Okay. All right, so now what is this sum? Well, this is the sum of geometric series again, right? But now the first term is 1 minus p. So that's 1 minus p over 1 minus 1 minus p. Right? And let's continue. Well, that's 1 over p. Well, surprise, surprise. That's exactly minus 1 over p squared. Sorry, I lied a little bit, right? It's really 1 over p minus, right? So let me show you. It's really This is 1 minus p over p. So that's 1 over p minus 1. Right? But derivative with respect to minus 1 is clearly 0. So right. Any question? All right. So that's, again, right? These are analytical derivation that at least, right, show you why the expectation is 1 over p. And again, right, it at least convince you that, right, unless you memorize this, you're not going to be able to pull this out of the hat. And the variance, right, well, it's just more complex, so we won't bother. There's a pattern to this. Not sure if the pattern is that meaningful, but it's actually a way you can memorize. Well, this is another way to write this is 1 over minus p squared. Who knows, right? These are the same thing. Sorry, this is 1 over p minus 1 over p squared. So, right. So may or may not be helpful, right? But anyway, so but we won't derive this because the analytical derivation is even more complex. But actually, right, the proper question to ask in this case is, right, similar to, let's say, the hypergeometric, right, the binomial, etc., right? Is there a probabilistic derivation of the expectation invariance, right? What we have shown you is the analytical derivation. So is there a probabilistic derivation? Well, the answer is yes, there is, but it will require the concept of conditional expectation or the law of double expectation, right? Which is the last topic of this class. So right now, right, even though there is a probabilistic way to do this, is a bit beyond the scope of what we have covered so far, right? So we will not show this. We'll come back to this, right, at the end of the class. Any question about this? Okay. All right. So the next natural follow-up to the geometric is the negative binomial. Okay. So the negative binomial is, first of all, it has this mass function. Why is it a natural follow-up to a geometric? Because just like the binomial, right, can be viewed as a generalization of the Bernoulli, the negative binomial is a generalization of the geometric. In the sense that, right, instead of waiting for the first success, you want to wait until you see the first n successes. So this n in here, right, is the parameter of the negative binomial. And that's why, right, the number of trials have to be at least n, or, right, the support of the random variable have to count from n upward. Okay. So now to explain the mass function, because if you don't, right, actually you won't memorize the mass function. You won't be able to memorize the mass function unless you understand why it is that way. So what's the picture here? The picture here is, again, right, you have basically a bunch of zeros, but you have a 1 somewhere thrown in, right, until the last one is a 1. Okay. The last one must be a 1 because that's how long it takes for you to get to how many successes you're waiting for. So the last one must be a success. Okay. And the length of the sequence is k, right? Because That's how long it takes you to get there. Among this, right, there are exactly n, right, ones, n successes. All right. So let's see what the probability of that is. Now this sequence, right, is not just any sequence of 0 and 1s, right? It's not a sequence of, let's say, n 1s and k minus n 0s, right? That's not that. The reason is, right, of the special positioning, right? The last one must be a 1. So that's fixed. However, right, before the last one, the remaining n minus 1, right? Basically the n minus 1 successes, right, before the last one can be anywhere, right, among the k minus 1 trials. So this is basically the positions of the first n minus 1 successes. Okay. So that's it, right? After that, right, this probability is self-explanatory, right? You want n successes and k minus n failures. So, but you have to choose, right, the positions of the first n minus 1 successes out of the first k minus 1 trials. Any question? All right. So as with, like, let's say some random variables, not all, there are different, let's say, parameterization, meaning that we or people are describing the same phenomenon, but they just choose to parameterize it differently because they choose to count different things. This is just like a fact of life that you have to get used to, right? So if you look at Wikipedia, or I don't know, AI, whatever you reference these days, you might see, let's say I don't know, right, call on ChatGPT and whatnot, and ask for a mass function of the negative binomial, NP, right? It may give you something that is not the same as what I give you. Okay? And then you might have legitimate reason to say that, well, that guy who teaches probability has no idea what he's talking about, right? Should resign. Well, the point is, right, may not, whatever the model, right, is giving you, ChatGPT is giving you, may not be the only way to describe the negative binomial. And so you have to be careful to explain, right, what you're counting and what you mean by n, for example. So n here represents a number of successes we're tracking. But there are some other ways to track the number of failures. Okay. So actually both of us track the number of successes. But some random variable, right? Another way to describe the negative binomial tracks the number of failures rather than total number of trials until you see the first success. All right. So the relationship is our definition, subtracting n would be their definition. But you can obviously see that the mass function, right, the way the parameters line up will not be exactly the same. Okay. And so again, with different ways to parameterize, it's not just for fun. There are advantages and disadvantages to different ways to parameterize. So their way or this way has the advantage of explaining the name negative binomial. Actually, it's a very interesting thing that you should look into if you're interested in combinatorics. Namely, right, it kind of explains to you and goes into the natural reason on why, for example, what would this be? Okay. Again, right, in the way we define things, -3 choose 4 is sort of like meaningless, right? But it turns out there's a sensible way to extend the definition to a negative number and connect it to, right? And that's where the negative binomial comes in. But I'll stop there, right? Because this class is not combinatorics class. We have no reason to extend our definition that far. And right, anyway, we choose, right, our definition to be this. So the point is we won't have a direct connection to negative binomial concept, okay? But our way is a probabilistic connection with the geometric, and that's more meaningful that way for us. And so, right, I just want to mention this, okay? But so for us, right, the definition is advantageous because naturally then a geometric is a negative binomial, right? And also a negative binomial is a sum of independent geometrics. This is very important. All right, how so? All right, so if we have IID geometric, then you sum this up, you will get a negative binomial. Right, is this obvious? Like, is this sum obviously a negative binomial, meaning is this relationship obvious? Does it just make sense? Or so I would say, right, that this is not that obvious. Well, it will be obvious if you look at it the right way. Okay, but what is that? The way you look at it the right way is actually through a sequence of independent time. So for example, right, if you look at the time until the first success, that's x1, right? Or actually, right, your grand total is, let's say you want to wait for n successes, right? However that is. But to get to n successes, you must first have to go through the first success, right? This is very, very reminiscent of counting up to, let's say, how many ways, how many customers you want, things like that. And then from there, right, once you get your first success, then you kind of forget about the sequence so far and start fresh. And then you get your second success. And then you forget again and you get your third success. And so on until you get to your last success. Right? But each block of zeros, right, counting from the last one, will be a geometric because of, you know, this kind of like a memoryless property. Once you get there, you kind of forget, right, in terms of how you need to keep track of, right, where you go going next, because the trials are independent. Okay. So in this sense, that's what is true. All right. So I think let's give you the quiz and we'll continue after the break. I think, let's see here. So for any interesting question? All right, so let's have this for the quiz today. Okay. Any question before we take a break? All right, we'll continue at 7:05. All right. Is there any question before we continue? Okay. So, right, we just mentioned that a geometric, right, is a sum of, a negative binomial is a sum of IID geometric, right, which then gives us, right, a very easy derivation or expectation, right, and variance of a negative binomial. Because, right, you just sum, you just expectation of the sum, right, and then it becomes the sum of expectation. And variance of the sum, while, right, not generally being the sum of the variance, here variances, here it is because they're independent. So we get this, right? So basically, once you know the geometric, then the negative binomial, at least, right, expectation and variance automatically follows. Any question? All right. So the last random variable, right, that we'll be discussing among the discrete random variables is a Poisson, right? Which is probably the most famous of them all, maybe behind the binomial, right? And so, first of all, the binomial has a pretty strange PMF, let's say, right? If you're not used to this, it probably has no rhyme or reason. And the support starting at 0, right, instead of 1, and has no upper bound, right? So it has infinite support. And let's talk about the model. The Poisson, right, is used to model the number of occurrences of rare event. And this actually may lead to wrong interpretation, right? Especially students who just dabble into probability, right? Loves to make statements about Poisson that probably makes no sense here and there. The first thing, right, you want to understand precisely is what does rare mean, right? Because, for example, right, the typical example, right, that would be used as a model for Poisson would be number of customers arriving at a store in an hour, right? Now, why would that be rare? But this might be a bit more, right, to the point. Well, supposedly, right, earthquake in California is rare, so, right. But also something that you might or may not think about is number of typos on a page of a book, right? So notice, what do they all have in common? They all have in common, right, as integer, right, is number of occurrences. Second, they all occur within a time window. Very important, right? You have to specify the time window. All right. And right. The third, which is really a modeling aspect here, is, right, if you use the Poisson to model it, then what you're committed to is there's no upper bound, okay, on the number of events, right, that can happen. Now, earthquakes, yeah, I can live with that, right? I mean, the probability that there'll be a million earthquake in California in 6 months probably is very small, right? Super small. But it's imaginable, whatever that means, right? A million earthquakes, so let's say 1,000, right? But clearly, right, there cannot be a million customers arriving within an hour in the mall. Well, I guess simply because, not even a million people, are there in the mall to begin with, or, in the city, etc., right? Same as typos, right? I mean, the number of typos in a page clearly, right, is bounded by how many letters are there in that page, right? So it cannot go on forever. So somewhere you already see the nature of a Poisson. And by the way, right, these are examples that are modeled by Poisson, right? I'm not making this up. So you legitimately can use Poisson, okay, to model all of these. But the thing, right, that you want to keep in mind is by what I just discussed, Poisson by its nature has something about approximation already. Approximation, right, in their definition, right? Because you kind of say that approximately the number of titles is Poisson-ish, because, right, like I said, it cannot go on forever, or Poisson will, right? Things like that. But of course, it's close enough for the ones that matter, meaning the ones that are starting out like 0, 1, 2, right? The probability. So let's explain the rare event, right? And then we'll go back to this. And then we'll go back to this too. Where does the rare come in? The rare will come in through this very important statement that the Poisson is the limiting distribution of a binomial. All right. But you have to be very careful here, because here we're kind of talking about an area of probability slash statistics, properly speaking, probability, called asymptotic distribution, right? So we let n goes to infinity, but not only that, we let p goes to 0. So here you have to be very careful, because if you don't have this, and you let n goes to infinity alone, then the approximation will be the famous normal approximation of the binomial, all right? Which probably you have heard more often about. The Poisson approximation has to require that p goes to 0. And that's your rare event. Because p, right, the success rate goes to 0. That's why we talk about rare event. Okay? But not only that, it's in such a way that the average, the mean, stays as a fixed constant. Okay, which is lambda, which is the parameter of the Poisson. And approximating in which sense? That means, right, the probability of the binomial np equals to k is approximately this when n is large, p is small, and n times p is approximately a constant. How large do you ask? Well, depends on the error, right, tolerance you want to admit. But let's say something like this. Let's say a binomial, 1,000. That's large enough for n. Let's say p is 0.0001, right? Or even 0.001, right? Is small enough, right? And of course, right, that means lambda equals to 1, right? And also let's point out, right, why an approximation is necessary or is valuable, besides the fact that the Poisson is, an important distribution in of itself, right? But it is important exactly through this kind of approximation. Just like the normal. The normal is important because it shines, right, through the central limit theorem, which is an approximation. So here, right, if you write down the probability, that's n choose k, right? Let's say k here is 500, right? That's 1,000 choose 500, 500 raised to, sorry. And then 0.999 raised to 500, okay? Now, I believe that I have seen students telling me what 1,000 choose 500 is on the exam. Maybe close to that. Any idea why? Any idea how? I'll let you figure that out, right? But I suppose that any human probably cannot figure out 1,000 choose 500, right? Very quickly.
Pascal's triangle if he just wrote it all out.
Yeah, remember on an exam. And well, since you're talking and I suppose you're interested, I'll give you 10 minutes. if you can tell me exactly 1000 to 500, I'll give you an A again. How fast can you write out a Pascal triangle? And actually, you know what? Let's be realistic here since we're talking. I think I can give you an hour if you honestly write down the Pascal triangle to get to 1000 to 500. You know why?
Well, it's not very mathematically meaningful though, I guess.
Of course not. But also, right, the more you write down the Pascal triangle, what happens? The more the length grows. It's not a
Yeah.
fixed, so no, right? It's physically impossible, I would say, to even do it within an hour, to just write down those numbers, forget the calculation. Okay. So no, I don't think they figure out the Pascal triangle. And then, right? So that's, but yeah, and you're perfectly right. It's completely meaningless what that is. And second, right? This, so this is very large. And this is very small, right? We know what happens when we multiply a very large number with a very small number. Errors. Errors are waiting everywhere. Because when you do that, even with a calculator, right, it will have some error, right? It won't not give you an exact number. This also will have error. And when you multiply these two together, right, that would be some bogus number unless you have a very precise calculator. Again, these days and age, yes, I can entertain the thought that, right, it can do it. But I think an intelligent computer, whatever, you try to plug in these days, will try to do some simplification, or behind the scene, it might already do an approximation. But right, these things, of course, are invented 2 centuries ago, where right, they don't have the luxury of ChatGPT like you do. So right, obviously, they still have to consider this kind of calculation. And so, right, an approximation is really, really useful for them. Right, that's the point. Okay. So now, having said that, right, let us. Oh, and also we will right look at the proof here when we look at the moment generic function at the end of the course. But now let's go back to the examples here and explain right why it's appropriate. So, why the number of earthquakes in California is a rare event? Again, I think that is probably the most digestible one, right? Because we readily accept that it's rare. But one way to think about it is, right, that basically you can look at, let's say, earthquake per month in California as a binomial distribution, right? Meaning each month is a, you know, binomial. Yeah, right. Each month is a binomial, right? And this, right, basically is probably very rare, right? P is a binomial with, P. So hold on. You know what? No, per month is not good enough. Sorry. Probably you want to reduce it down to a day, something like that. The earthquake, right, per day in California, and you just look at the chance of it, right? Chance of earthquake per day in California is very rare, right? It's close to zero. Okay, let's say. And then, right, you look at over the range of 6 months, which is how many days? Well, it's only 180 days, right? Not that many. But you can see, right, that's kind of enlarged P small. And of course, you can push this per day, right, estimate into per hour, that kind of thing. And then you will get, right, more, right? This is N here, and this is P, right? You get that kind of calculation. But basically, right, within any time, a small time window in California, right, the chance of earthquake is super rare. And then you add that up over a long interval, right? You get a Poisson, right? Let's explain the customers here, right? Like I said, right, off the surface of it, it's kind of strange to think that number of customers arriving at a store as a rare event. What's rare about it? But what's rare or how this might be legitimately a Poisson approximation is something like this. You look at the total number of customers in the mall, right? That's large, right? I don't know, a couple thousand, I don't know, a day or something like that, 10,000. And then each of them, right, has a very small chance to visit a store, right? I mean, of course, again, right, it depends on your store, but individually, each of them, right, at the mall probably have a very small chance of visiting the store. So when you sum over all these customers, right, then you have the total number of people visiting your store. So it can be approximated, right, as a Poisson, right, as a binomial with n large p small. Same thing with the typos here, right? What you're looking at is the chance of a letter being a typo is small, right? A word, right, being a typo is small, right? And then if you look at the book, that it has a lot of words, right? So n large in that sense. You look at the whole book, right? That has a lot of words. Each word has a small chance of having a typo. So in that sense, right, you sum it up over a large number of words, you will get a Poisson, right? But nevertheless, for example, right here, let's say, but you're really talking about number of typos on a page, right? What's going on there? What's going on there is the Poisson here has a flexible scaling, okay, behavior due to this time window, right? Argument. For example, right? Say the number of earthquakes in California in 6 months, right? Let's say it's a Poisson 2, right? What I mean is, on average, right, there are 2 earthquakes, right, in 6 per half a year in California. Well, with that said, is it possible for me to model the number of earthquakes in California in 1 year? Do I know what distribution it follows? What about in 1 month? Do I know? The answer is yes, I do, right? Just scale it up. Would in 1 year, that will be a Poisson 4. In 1 month, it will be a Poisson 2/6. You understand? So, right, that's why, for example, once you have the number of typos in a book being a Poisson, you can scale it down to a page. But again, right, probably, again, this page probably should have a lot of words to make the approximation good. But that's where, right, things are, right? You have to kind of see, you know. Okay. Any question here? So that's where rare comes in. All right. So this is just a fun connection. Oh, sorry. I still haven't explained, right? This. All right. So let's calculate the expectation, right? So the expectation of a Poisson, right, will be the sum k e to minus lambda, lambda to a k for k factorial, k from 0 to infinity, right? And why would that be why would that be equal to lambda? Well, it's obvious that we want to cancel here, right? But notice k start from 0 doesn't contribute to the sum. We can move the sum to 1, right? And it's clear that we want to match up the k minus 1 here, right? By pulling out lambda. And of course, right, that factors out, and we can change everything back to a sum over 0, right? And this sum from your Calc 2 education would be e to lambda, right? All right. So that explains this. What about the variance? Well, right, the variance requires a harder calculation, right? But here is a way to explain it using the definition. Oh, sorry, the approximation, right? Notice for a binomial NP, right, then expectation is NP, and variance, right, is NP1 minus P, right? Notice NP is lambda, which is exactly the expectation of the Poisson, which makes sense because we claim the Poisson approximates this, so expectation should match, right, or converge to each other. What about variance? We should expect the variance matches as well, right, in the limit at least. But how does it match in the limit? Notice, right, that n times p goes to lambda, so that goes to lambda. What about 1 minus p? Well, p goes to 0, so 1 minus p goes to 1. So actually, the variance here also converges to lambda, right? So this is a more sophisticated argument, but right, it explains why expectation and variance of the Poisson are the same. You can do it through an analytical calculation, but this is an alternative explanation. Okay. Any question? Oh, right. Okay. So now back to the hat problem. Right. This is exactly, remember, at some point where we said, right, it's not relevant to that problem at that time, but this sum converges to e to minus 1 as n goes to infinity. And now, right, in terms of this current discussion, this is relevant because this is probability of a Poisson 1 equal to 0. And also notice, right, this x here has constant expectation equals to 1, right? We explained that previously, right, using the linearity of expectation. So in fact, right, this is again a case of like a small dependence, right, between the trials. So these are not independent trials because the individuals, right, receiving their own hat are not independent. But as n grows larger, right, this, I guess this structure, the dependence, I guess, gets weaker or something like that. And basically, eventually, right, this can still be approximated using a Poisson. Okay. But the reason here is much more sophisticated than this. This is already sophisticated, mind you, right? It requires a moment-Jane function technique. But this is even more sophisticated because, right, it's a dependent approximation, right? But the Poisson is still a present, right, behind a presence behind the hat problem. But just that's for fun. Right? This is beyond our class to get into. Okay. All right. So this is so before we get to the problem set, right? A recap is right. So while we kind of went over, right, you know, a good 5 or 6 of them, that in no way, right, exhausts all possible random variables. The most obvious reason is, right, if I give a list, you can always come up with something outside the list, right, by being inventive. So no way, right, we can exhaust all the lists, and there's no reason why. The reason why these are common or popular, as I repeat, because they represent some sort of very fundamental, right, experiment that you see everywhere, right? The binomial, notice, yeah, right, a lot of them actually spring from the binomial, right? The binomial, the hypogeometric is kind of a close cousin. The Poisson is an approximation of binomial. The geometric also sort of somehow has that flavor, right? And the negative binomial, right? The word says it all. That's why, right? These are kind of all popular from that point of view. But, right, you are very, very likely, right, to encounter something you haven't studied before, right? If you, after this class, right, there's Math for 81 at Rutgers, where, for example, you can look at the sample variance, right? I should use capital X. Right, like this. So if you have, let's say, xi, iid, I don't know, right, Bernoulli, p, then the sample variance is going to be a discrete random variable. Well, what is it? What distribution does it have? Answer, no name, right? There's no name given to it. So it's just a sampling distribution of the sample variance. So, right, given a not studied before random variable, which will happens when you study statistics and things like that a lot, or naturally, you just kind of have to start from scratch. What's the support? What values can it take? Can I write down a mass function? Can I find expectation and variance? That actually is the thing that people always do with sample variance. Can I calculate higher moments? Can I find its moment sharing function? Right? But basically, these are just roughly some questions you want to start asking to get to know the random variable, right? So that's the point, that basically, given a random variable, it's not like you just sit there and say, I know everything, right? Studying that random variable could be a work of an hour, a day, a week, a couple months even, right? To say something intelligent about a random variable. Okay. All right. So let us continue with the next problem set. Okay. So I guess starting out, right, we'll still deal with binomial distribution, but in I guess, a slightly more advanced context, combining it with the law of total probability. All right. So how do we solve this question? So first of all, there is a random variable, right, that we need to be interested in, right, which is what? the number of components, right, functioning, right? What do we know about this random variable? Any suggestion? So on a rainy day, right, each of the components independently functions with probability P1. What does it tell us about the distribution of the number of components functioning? So that looks like a binomial and P1, right? If it runs. And then similarly, that would be a binomial and P2 if it doesn't ring, right? And then how do we combine it to answer this question? How do we find the probability of the satellite function? Any suggestion?
Well, would it be like P P1 uh to the kth power times 1 minus P1 times n minus kth power, and then do the same for P2 and then add them together?
Like this?
I I think so.
No. First of all, right, that doesn't follow the binomial distribution, right? And second, that doesn't follow the statement of the problem. At least K.
Oh, oh, I misread that. Yeah.
No worries. But even without that, right, the binomial distribution is not just that. The binomial distribution would need and choose K in front, right? So, but even that is incorrect. Forget the at least, right? Because there's the rain and not rain interacting, right? And that's where the law of total probability comes in. So we need to split this into cases, function, given rain times P rain plus P function, given not rain times P not rain. And so rain is alpha, right? What about function? Function here, we identify, right? So now if we're rain, then we know that we're going to have a binomial. So we can say there's P of a binomial and P1 be going to go to K. Like that. And now finally, we can use the binomial expression. to finish the problem. Any question? All right, let's continue. All right, so what random variable that we need to track here? Is there a quantity we want to track in this problem? So, right, the number of votes, the number of, I guess, guilty vote, right? You can call it that way. Is the random variable we're interested in, right? Now, similar to the previous question, right? What do we know about X? What distribution does X have? Any suggestion? there are 12, right? Trials. But what are the success probability? What is the success probability? So votes a guilty person innocent, right? So that's a non-guilty vote, right? So I think if we want guilty, then it should be 0.8 if person is guilty. And it will be 12.1, right? If a person is not guilty, right? Any question on this? All right. Do we have enough information to answer part A? What's the probability of a correct decision? How can we do this? What should we do with this expression? So just similar, right, to the previous calculation, we should split it into the cases, right, where we would know the success probability of the binomial. In other words, right, here we should look at as correct decision condition on person being guilty, right? Times probability that the person is guilty plus probability correct decision given that the person is not guilty times probability that the person is not guilty, right? And we are told that 65% of the person is guilty, so we can replace it with probability correct decision given guilty times 0.65 plus probability correct decision given not guilty right, times 0.35. Any questions so far? And how can we continue with this calculation? How do we calculate the probability that the decision is correct if a person is guilty? Similarly, how do we calculate the probability that the decision is correct if a person is not guilty? Well, it takes at least 9 votes, right, to convict a defendant. So if a person is guilty, then they need to be convicted, correct? So that would be probability of a binomial 12.8 equal to 9. But if a person's not guilty, then they should not be convicted, right? And so that would be right. And now we can plug in the expression. Like that. And that will be the answer for part A. Any question? Okay, so I think this is a good place to stop for today, and we will continue on Wednesday. Okay.